Triton, one of Neptune's 13 moons, was discovered in 1846 by British astronomer William Lassell. Triton has a unique retrograde orbit around Neptune, meaning that it rotates in the opposite direction of the planet. Regardless, only one side of Triton is visible from Neptune due to the synchronous orbit of the moon, similar to Earth's own moon. Triton is thought to have been an object captured by Neptune's gravity from the Kuiper belt. Thus, we propose to focus our mission on observing the interior composition of the moon.
Triton's surface and atmosphere was visible from a pass-by of NASA's Voyager 2, the only mission that has flown by Neptune and its moons, including Triton. From these images, we have found that Triton's surface is lightly cratered and shows evidence of volcanic activity. This evidence consists of smooth volcanic plains. Triton has a very thin atmosphere which is composed of mostly nitrogen and methane gas. Triton's southern pole is covered in an ice cap, red in color, made primarily of nitrogen and methane gas. This is thought to be because of the volcanic activity that takes place on the satellite surface. Not much is known about the interior of Triton, but it is thought to contain more rock than the icy moons of Saturn and Uranus.
Triton is also one of the only geologically active satellites in our solar system. It has active geysers of liquid nitrogen, which were found by the Voyager 2 mission in 1989. This is one of the primary reasons that the surface of the satellite is fairly young in comparison to the other objects in our solar system.
Triton's diameter is 2,700 kilometers and has a density of about 2.05 grams per cubic centimeter. Triton is one of the coldest measured objects in our solar system, measured at negative 391 degrees Fahrenheit or negative 235 degrees Celsius. This leads some astronomers to believe Triton looks similar to Pluto. Triton's axis of rotation is tilted 157 degrees, and its orbital rotational period is about 6 days. The idea of Triton being a captured object is supported by the eccentricity of Nereids' orbit as well as by the low number of satellites around Neptune.
Triton is commonly thought to be a captured moon of Neptune. It was only viewed previously by passing of Voyager 2. We know that by focusing our mission on the internal composition of Triton, we will be able to compare what we know about Neptune's other 12 satellites, as well as what we know about the other Jovian moons. As mentioned previously, all that is suggested about Triton's interior is that it is icy and rock compositions. Referring back to the captured Kuiper belt object theory, we would also be able to compare Triton to the other objects in the Kuiper belt, and contrast those findings with the interiors of Neptune's moons.
The total budget for this proposed mission is $250 million. $175 million is designated to going towards the cost of the mission launch itself, spacecraft construction, and the monitoring of the craft while it is in space. The budget also includes the cost it will take to reach out to the public with educational and informative activities. The informal aspects will include a newsletter as well as multiple inspirational events. This leaves us with $75 million to spend on instruments that will be beneficial to the proposed mission. The instruments that we will use is dual imaging systems that cost $20 million, X-ray spectrometers that cost $20 million, and the infrared spectrometer costing $30 million, which in all costs $70 million.
Our proposed mission to Triton is primarily to study the interior of the satellite. Since it is thought that Triton is a captured moon, likely from the Kuiper belt, this mission will surely give us a better idea on where exactly the object is from. If it did not form around Neptune like its other 12 moons, the instruments we will be using are the dual imaging system, the X-ray spectrometer, and the infrared spectrometer. We will be using the dual imaging system for taking X-rays beneath the surface of Triton. This will give us a better idea what could be deeper in the core and possible compositional makeup. The X-ray spectrometer will identify the atoms and elements that reside beneath the surface. This instrument will also identify the chemical composition of the core. Lastly, we'll be using the infrared spectrometer. This instrument will be essential in identifying the core elements and composition of Triton. This instrument measures infrared energy from the inside of planets and satellites, revealing its geologic activity. Educating children and reaching out into the community to inform the public about our solar system and the mission we are trying to accomplish is important. There is a newsletter for the public that explains what we are trying to accomplish by going to Triton. This newsletter includes our reasoning for the mission as well as we hope to find out by conducting experiments on this moon. The public can also be informed of our mission by attending one of our many informational events we will be having, raising awareness on uncovering more information about our solar system. Funding for our newsletter will be included in the cost taken out of our original budget. Since not much is known about Triton, we feel the public should definitely be well informed before the proposed mission.
In conclusion, with our mission, we hope to discover more on the composition of Triton,